Welcome back to Petrole-um, a student course survival guide. I'm your host, Mina Donishvar, and we're here to make learning petroleum just a little bit easier. Today's topic is that of viscosity. So let's begin with a story that happened 100 years ago. On January 15th, 1919, in Boston, Massachusetts, 24 million pounds of molasses burst forth from a factory, Purity Distilling Co., and flooded the streets at approximately 35 miles per hour, killing 21 people and injuring 150 people. Now, I can still hear my high school gym teacher yelling at us on the track that we're moving slower than molasses. So, how did the molasses that day move so fast, actually kill people, and do this? A fluid property called viscosity. Viscosity is how resistant the fluid is to motion. So the higher the value, the lower the ability to flow. Fluid motion occurs when shear force is applied to the fluid. And if we look at the flow between two plates, we can see how this motion occurs. At step 1, the fluid is at rest. Y represents the distance between the plates. At step 2, the upper plate begins to be moved by a force F, an average velocity of u bar. After a short amount of time, the velocity profile builds between the plates. Once the flow stabilizes, the final velocity profile is thus. Now if I'm moving a little fast, this is a video. You can pause, rewind, take as much time as you need, but I'm going to just keep on going. The magnitude of the fluid velocity is related to the magnitude of the shear stress. So a proportionality constant is used to encompass that relation, which is called viscosity, and is represented by the Greek letter small mu. The dynamic viscosity is defined as thus. Don't let that P to E scare you. It's just the velocity gradient in any direction. This simplifies down to the shear rate term, gamma dot, and referring to flow over a plate, we can see how this is defined, and is the apparent viscosity. The units on this can get a little confusing, so let's run through that really quick. Using SI base units, the apparent viscosity equation becomes Pascal seconds. A unit called poise, named for Jean Poiseuille, is introduced to account for the scaling values and simplifying the ending unit. This is further scaled down to the most commonly seen unit of centipoise. Here's a list of common liquid fluids and their absolute viscosity in centipoise, as well as their specific gravity. You'll see soon why the presence of the temperature that the viscosity was measured at helps validate the data, and why that's a necessary column. We'll also cover the meaning of that final column, viscosity type. But for now, another viscosity term that is often used is that of kinematic viscosity. This is the dynamic viscosity divided by density, either represented by mu sub k or by lower epsilon. The unit most often used to describe this is that of centistokes, named after Sir George Stokes, which is defined as the kinematic viscosity of a fluid with 1 cp of dynamic viscosity and the density of 1 gram per cubic centimeter. Behavior of a fluid's viscosity is also dependent on the type of fluid in question. A Newtonian fluid, which is the most common, such as water, air, alcohol, glycerol, and thin oils, shear stress is directly proportional to shear rate. This forms a linear relationship that is only valid for laminar flow. We haven't defined what laminar flow is yet in this series, but a video on the Reynolds number, which will include such definitions, is coming soon. Other fluid types and models that you might come across are going to be covered, but this Newtonian model should get you pretty far. A fluid's behavior can be characterized based on if a fluid is dependent on shear time, or both. An example of a shear-dependent fluid you might see a lot is the Yield-PsuedoPlastic fluid. Here, apparent viscosity decreases with increasing shear rate, as shown. Another shear-dependent fluid is the dilatant fluid, in which apparent viscosity increases with increasing shear rate. A shear time-dependent fluid, such as a Thixotropic fluid, viscosity decreases with time after the shear rate is increased to a new constant value. And this means that the viscosity can return to another value just over time if it's left alone or at a different shear rate. A Rheopectic fluid, viscosity increases with time after the rate is increased to a new constant value. Some non-Newtonian models you might want to be aware of are the Bingham plastic model. Flow will not occur until a shear stress exceeds the yielding shear stress, and then the changes are proportional. That means that this fluid isn't going to move until a certain amount of force is applied to it, and then it'll start moving. And once this happens, the relationship is linear, and you can assume a Newtonian-like behavior to help simplify your calculations. Power law fluid model is also important, and you might see it. This one adds a consistency index K and a parameter N to characterize the fluid. The Herschel-Buckley fluid model combines the two, the Bingham plastic and the power model, to create this model, and it's also dependent on the fluid type. How a fluid's viscosity behaves is also dependent on the pressure and temperature. Due to how molecules act, a liquid's PVT relationship is slightly different than that of a vapor. Liquid water's viscosity increases with pressure, but decreases with temperature. In other words, as temperature increases, viscosity decreases, and this should make sense if you've ever put a honey jar in the microwave before using it. Now, if you remember our beginning story, the Boston Massacre. It happened in January, on a day when temperature soared from the usual and previous winter chill. The tanks failed, also due to the temperature rise, but that's another topic. The heated molasses became fast and dangerous. In gas, as pressure decreases, the molecules are farther apart and slip past each other more easily. I don't want to focus on the shape of this plot, as it'll make more sense in more application-focused topics. But I hope you enjoyed and learned something. As always, thank you for watching. Please like and subscribe to our channel. And if you have any questions, concerns, you can email us at petrole-um.studentsurvival@gmail.com. Thank you.